On the morning of December the 20th, 1944, Oberleutnant Klaus Hartmann stood in a reinforced bunker outside Malmedy, Belgium, watching his company prepare for another assault on American positions. Hartmann was 26 years old, a veteran of the Eastern Front, and he had seen artillery kill thousands of men. He knew how to survive it. He had trained his soldiers in the fundamental principle that had kept German infantry alive since 1914. When you hear the whistle of incoming shells, you have 3 seconds. Get to your foxhole, get behind cover, get below ground. The shells will impact, explode on the surface, and if you are deep enough in your trench or bunker, the shrapnel will pass harmlessly overhead. It was December 20th in the Ardennes, the 5th day of Germany's massive winter offensive. The weather was terrible. Thick clouds at 500 feet. Visibility less than a mile. No American observation aircraft could fly. The American artillery would be firing blind, setting timed fuses based on guesswork. His men would have plenty of warning. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Hartmann gave the signal. 140 German infantry rose from their positions and began advancing across the frozen field toward the tree line 300 yards distant. They moved in loose formation. Experienced troops who knew to disperse, who understood that concentrated groups drew concentrated fire. Within 30 seconds, the first American artillery rounds arrived. But there was no whistle, no warning. The shells simply detonated 70 feet above the ground, directly over the advancing formation. 140 men were caught completely exposed in the open. Hartmann, watching from his bunker, saw the entire line dissolve into a mist of blood and shrapnel. The few soldiers who tried to dive for cover found that cover meant nothing. The explosions were overhead, raining fragments straight down. Trenches became killing zones. Foxholes offered no protection. In less than 10 seconds, more than 80 of Hartmann's men were dead or dying. The survivors, those few who had been at the extreme edges of the barrage, ran back toward German lines. Some were screaming, others simply ran with their hands raised, trying to surrender to artillery fire. Hartmann could not understand what had happened. The American shells had not impacted the ground. They had detonated in mid-air with perfect precision, as if someone had calculated the exact moment when they would be overhead, but that was impossible. The weather prevented observation. American forward observers could not see German positions. There was no way to set timed fuses accurately. What Hartmann did not know was that his men had just been killed by a technology that Germany's best scientists had declared impossible to build. A miniature radar transmitter packed into the nose of an artillery shell. A device so sophisticated that even when German engineers captured 20,000 of them 3 days earlier, they had examined the fuses, studied the circuitry, and failed to recognize what they were looking at. That this is the story of how American physicists solved a problem that had defeated German, British, and Japanese researchers for more than a decade. How they created vacuum tubes that could survive acceleration forces 20,000 times the force of gravity, and how that technology killed tens of thousands of German soldiers who never understood what was killing them. The problem started with a fundamental limitation of artillery warfare. Throughout World War I and into World War II, artillery shells detonated in one of two ways. Contact fuses exploded when the shell struck something solid, the ground, a building, an aircraft, if you were extraordinarily lucky. Time fuses exploded after a predetermined delay, set manually before firing. A gunner would estimate the time required for the shell to reach the target altitude, set the mechanical timer in the fuse head, and hope the calculation was correct. For anti-aircraft fire, this system was nearly useless. Aircraft moved fast and maneuvered unpredictably. Setting an accurate time fuse required knowing the exact altitude, speed, and direction of the target. Even with sophisticated mechanical calculating systems, the best anti-aircraft batteries in 1941 were missing far more than they hit at Pearl Harbor On December 7th, 1941, American anti-aircraft guns fired thousands of shells at Japanese aircraft. The shells were equipped with time fuses set to detonate at estimated altitudes. Most detonated too early or too late. Worse, many shells that were set incorrectly struck the ground in downtown Honolulu and exploded there instead, killing 48 American civilians. The shells that did explode at the correct altitude rarely hit anything. Aircraft were small targets moving at 200 miles per hour, changing course constantly. A shell that detonated 20 yards away did nothing. A shell that detonated within 5 yards might damage an aircraft. Only a direct hit would reliably destroy one. The statistics from early war anti-aircraft operations were grim. American and British gunners needed thousands of shells to destroy a single enemy aircraft. In some engagements, the ratio reached 20,000 shells fired for every aircraft destroyed. That was not air defense. That was ammunition expenditure. For ground artillery, the problem was different but equally fundamental. A shell that detonated on impact with the ground directed most of its explosive force into the earth. Troops in trenches, foxholes, or behind cover were protected. The shrapnel pattern from a ground impact shell was horizontal, not vertical. Soldiers who went to ground survived. This had been true since the First World War. German infantry doctrine emphasized immediate dispersal when artillery fire began. Take cover behind any obstacle. Get below ground level. Wait for the barrage to end. Casualties from artillery were significant, but manageable if soldiers followed proper procedure. What military planners wanted was a shell that would explode in the air above the target. An airburst shell would direct its fragmentation pattern downward. Trenches would become death traps, foxholes would offer no safety. Soldiers behind cover would find that cover meant nothing against shrapnel falling from above. The concept was understood. Multiple nations had explored proximity fuses during the 1930s. A proximity fuse would automatically detonate the shell when it sensed it was near a target. No manual timing required, no guesswork. The shell would simply explode at the optimal moment. The engineering challenge was that this required putting sophisticated electronics into the nose of an artillery shell. Artillery shells experienced forces that destroyed any conventional electronics instantly. When a 5-inch naval gun fired, the shell accelerated from 0 to 2,800 feet per second in the length of the gun barrel. That created a setback force of 20,000 Gs, 20,000 times the force of gravity. Simultaneously, the rifling grooves in the gun barrel spun the shell at 25,000 revolutions per minute to stabilize its flight. Any vacuum tubes inside the shell would experience crushing acceleration and violent rotation. Standard vacuum tubes shattered under these conditions. The glass envelopes cracked, the filaments snapped, the tube elements came loose and destroyed the circuits. German scientists had been working on proximity fuses since the early 1930s. By 1944, they had explored more than 30 different approaches. Acoustic fuses, triggered by engine sounds. Electrostatic field detection systems, radio frequency proximity sensors. None worked reliably. In 1943, German engineers at Rheinmetall-Borsig concluded that building a vacuum tube-based radio fuse for artillery shells was technologically impossible. The acceleration forces would destroy any vacuum tubes small enough to fit inside a shell. The problem could not be solved. They halted their research program. British scientists reached a similar conclusion. Starting in 1939, researchers at PIE Limited began developing ruggedized vacuum tubes for proximity fuses. By 1940, they had working prototypes for unrotated projectiles, the British cover name for solid-fueled rockets. Rockets had relatively gentle acceleration compared to artillery shells fired from guns. The British fuses worked adequately in rockets, but attempts to adapt them for high-velocity artillery consistently failed. The tubes shattered. The circuits failed. The fuses were unreliable. In August 1940, a British technical mission led by Henry Tizard arrived in the United States. They carried a black metal deed box containing Britain's most secret military technologies. The cavity magnetron that would enable effective radar, design specifications for jet engines, and circuit diagrams for proximity fuse prototypes. The British had solved part of the theoretical problem, but could not manufacture fuses reliable enough for mass deployment. They hoped American industry could solve what British researchers had not. The National Defense Research Committee assigned the proximity fuse project to Section T, led by Dr. Merle Tuve at the Carnegie Institution in Washington. Tuve was a physicist who had helped develop the theoretical foundations for radar during the 1920s. He understood immediately that the core technical challenge was not the concept, but the execution. A radio proximity fuse was conceptually simple. A miniature transmitter in the nose of the shell emitted radio waves. When those waves reflected off a nearby target, a receiver circuit detected the reflected signal and triggered a detonator. The concept was straightforward. The engineering was extraordinarily difficult. Tuve assembled a team of physicists and engineers. The Navy gave him an impossible deadline. They needed working proximity fuses for 5-inch anti-aircraft guns as soon as physically possible. Japanese air power was destroying American ships in the Pacific. Without effective anti-aircraft defense, the Navy could not operate. Section T had months, not years, to solve a problem that had defeated British and German scientists for more than a decade. The team included some of the most capable minds in American physics. Richard Roberts and Henry Porter worked on circuit designs. Robert Broad developed receiver sensitivity systems. Harry Diamond and Wilbur Hinman from the National Bureau of Standards created specialized fuse designs. Every member understood the urgency. American sailors were dying while they worked. The first breakthrough came from modifying existing technology rather than inventing entirely new systems. Lloyd Berkner, one of Tuve's engineers, developed a design using separate transmitter and receiver circuits instead of a combined transceiver. This simplified the electronics and improved reliability. But the vacuum tube problem remained unsolved. Standard vacuum tubes could not survive artillery gun firing forces. The solution came from an unexpected source. Western Electric Company and Raytheon manufactured miniature vacuum tubes for hearing aids. Hearing aid tubes were already ruggedized for portable use in civilian applications. They were small, mechanically robust, and used relatively little power. Working with Tuve's specifications, Western Electric and Raytheon engineers modified hearing aid tube designs to survive artillery acceleration. They reinforced the glass envelopes. They redesigned the filament mounting systems. They tested prototype tubes by firing them from air cannons into solid blocks of wood, subjecting them to acceleration forces exceeding combat conditions. Most tubes failed. The engineers redesigned them and tested again, failed again, redesigned again. By January 1942, after months of iterative testing and failures, they had vacuum tubes that survived 20,000 G-forces and 25,000 RPM spin rates. The tubes were tiny, barely larger than a rifle cartridge. Each proximity fuse required 5 of these miniature tubes, along with resistors, capacitors, a battery, safety mechanisms, and a detonator. All of this had to fit into a space smaller than a beer can and weigh less than 2 pounds. The battery system presented enormous challenges. Standard batteries could not withstand firing shock. Engineers developed a reserve battery activated by the setback force of firing itself. A small glass ampule containing electrolyte would shatter when the shell was fired, activating the battery at that moment. This solved both the storage problem and ensured the battery would only activate when needed. Safety mechanisms required equally innovative engineering. The fuse had to remain completely inert during handling, transportation, and loading into the gun. It could not arm until the shell had traveled far enough from the gun to ensure friendly forces were not endangered. Engineers designed a complex system using mercury switches that required centrifugal force from the shell's rotation to close, combined with a timer that ensured at least 0.3 of a second elapsed after firing before the fuse could detonate. This meant the shell had to travel at least 750 feet from the gun before it became active. Even if a shell misfired and fell near the gun crew, it would remain completely harmless. In early August 1942, the Navy conducted the first live fire test in the Chesapeake Bay. The cruiser, USS Cleveland, fired proximity-fused shells at radio-controlled drone aircraft on August 12th during its shakedown cruise, Gauss. The test was scheduled for 2 days. It ended after 1 day because all available drones had been destroyed. Cleveland's gun crews fired 4 shells. 3 drones were destroyed. Navy observers were astonished. The proximity fuses worked perfectly. For the first time in history, anti-aircraft gunners could reliably hit moving aerial targets without requiring direct hits. The shells just needed to pass within 70 feet of the target. The proximity fuse would detect the aircraft and detonate automatically, shredding it with shrapnel. The improvement over time-fuse shells was dramatic. Some Navy officers initially suspected the test had been rigged. Subsequent tests confirmed the results. The proximity fuse represented a genuine breakthrough. But successful testing and combat deployment were different problems entirely. Tuva's team needed to scale up from prototype production to mass manufacturing millions of fuses. By January 1943, Section T had reorganized as the Applied Physics Laboratory under Johns Hopkins University, with Tuve as director. The project now involved 26 contractors and 10,000 workers. More than 100 American companies contributed to proximity fuse production. General Electric, RCA, Raytheon, Sylvania, Westinghouse, Eastman Kodak, Zenith, even Wurlitzer, the organ manufacturer. Each proximity fuse contained 130 miniaturized electronic components. Assembly required precision work performed by thousands of workers across multiple factories. These workers built the fuses without knowing what they were building. Security was absolute. The project had the same classification level as the Manhattan Project developing the atomic bomb. Workers who asked what the fuses were for received only vague answers about critical war materials. Most never learned the truth until after the war ended. The Crosley Corporation in Cincinnati became one of the largest proximity fuse manufacturers, producing 5.2 million units, roughly 24% of total wartime production. Crosley converted its barrel organ factory into a fuse assembly line. General Electric's Christmas tree lamp factory in Cleveland was retooled to produce miniature vacuum tubes. At peak production, American factories manufactured more than 100,000 proximity fuses per week. Manufacturing efficiency improved dramatically. The fuses cost $732 each in early 1942. By 1945, the cost had dropped to $18 per fuse. That price reduction reflected improved manufacturing techniques and the economies of scale that only American industry could achieve. In November 1942, the Navy shipped 5,000 proximity fuses to Pearl Harbor. The Pacific Fleet began distributing them to ships operating in the Solomon Islands. But the fuses came with strict restrictions. They could only be used over open water, where dud shells would sink to the ocean floor. If a fuse failed to detonate and fell on land, Japanese or German engineers might recover it and reverse engineer the technology. That risk was considered unacceptable. The restrictions were tested immediately. On January 5, 1943, Japanese dive bombers attacked American ships off Guadalcanal. After dropping their bombs, the aircraft pulled up and began climbing away. Lieutenant Red Cochran commanded the aft 5-inch battery on the light cruiser USS Helena. He ordered his gun crews to fire 3 salvos with proximity fuse shells at the departing dive bomber. The gun crews had minimal time to aim. The aircraft was already several thousand feet away and climbing fast. All 3 shells exploded in the air near the target. The dive bomber disintegrated and fell into the ocean. Helena's crew had achieved the first confirmed kill of an enemy aircraft using a proximity fuse shell in combat. It was not luck. It was repeatable technology. Over the next 12 months, effectiveness in naval combat became undeniable. In 1943, Navy ships fired 9,128 proximity-fused rounds and destroyed 61 enemy aircraft. That was one kill for every 150 shells fired. The old time-fused shells required 508 rounds per kill. The proximity fuse was more than 3 times as effective. And as gun crews gained experience and fire control systems improved, the kill ratios improved further. By 1944, proximity fuse shells were standard ammunition throughout the Pacific Fleet. Navy studies showed dramatic effectiveness improvements. Ships using proximity-fused ammunition were 5 to 10 times more effective at stopping attacks than ships using conventional ammunition. Admiral Arleigh Burke, who commanded destroyers in the Solomon Islands campaign, later wrote that mechanical time fuses only brought down enemy aircraft at night by accident. The proximity fuse changed everything by making nighttime air defense genuinely effective for the first time. On May 11, 1945, the destroyer USS Hugh W. Hadley was on radar picket duty off Okinawa when more than 100 Japanese aircraft attacked in a coordinated strike. Hadley's 5-inch guns were equipped with proximity fuses. In 90 minutes of continuous combat, Hadley shot down 23 aircraft, setting an all-time U.S. Navy record for a single engagement. Every proximity fuse shell that passed within 70 feet of a target detonated automatically. Aircraft could not evade an invisible sphere of death surrounding American ships. But while the Navy used proximity fuses extensively in the Pacific, the Army was prohibited from using them over land in Europe. The restriction remained in place through 1943 and most of 1944. Army artillery officers knew the technology existed. They had heard reports from the Pacific. They understood proximity fuses would be devastatingly effective against ground targets. A conventional artillery shell detonated on impact with the ground. Troops in trenches, foxholes, or behind cover were protected. But a shell that detonated 70 feet above them would spray shrapnel downward into their positions. Trenches would become death traps. Foxholes would offer no safety. Even log-reinforced bunkers could be penetrated by high-velocity fragments falling from directly overhead. Proximity-fused artillery would multiply the lethality of American firepower many times over. But Pentagon officials feared that even a single dud shell falling into German hands could compromise Allied air superiority. Germany had the most advanced scientific establishment of any Axis power. If German engineers reverse-engineered the proximity fuse, they might develop countermeasures that could blind Allied radar systems. Or worse, they might create their own proximity-fused anti-aircraft shells that would devastate Allied bomber formations over Germany. The risk seemed too great. Army artillery would have to wait. That calculation changed on June 12, 1944. Germany began launching V-1 cruise missiles at London. The V-1s were jet-propelled flying bombs, pilotless aircraft packed with explosives aimed at civilian targets. They flew low and fast, approaching speeds of 400 miles per hour. Traditional anti-aircraft guns could rarely hit them. The V-1s were too small and too fast for accurate time fusing. British fighter pilots tried shooting them down or tipping their wings to send them off course, but it was dangerous work. The V-1s killed tens of thousands of civilians and caused massive damage to London. The Pentagon authorized limited use of proximity fuses to defend London on June 12, 1944. Initially, the fuses were restricted to 90mm anti-aircraft guns and British 3.7-inch guns positioned along the English coast where Duyud shells would fall into the ocean. The results were immediate and dramatic. In the first week of operations, anti-aircraft guns destroyed 17% of incoming V-1s. Within a month, as gun crews gained experience, the success rate climbed to 79%. By late August, proximity fuse shells were accounting for 82% of all V-1s destroyed on some days. The Germans launched 9,300 V-1s at England between June and August. Without proximity fuses, the casualties and destruction would have been catastrophic. British Prime Minister Winston Churchill later called the proximity fuse potent against the small unmanned aircraft and credited it with preventing far greater loss of life. When V-1 attacks shifted to the port of Antwerp in September 1944, restrictions loosened further. Antwerp was critical for supplying Allied armies advancing into Germany. Losing the port would cripple the offensive. Between October 1944 and March 1945, Germans launched more than 8,000 V-1s at Antwerp. Anti-aircraft units equipped with proximity fuses destroyed more than 2,000 of them. The port remained open throughout the war. On October the 25th, 1944, the combined chiefs of staff authorized general use of proximity fuses over land for anti-aircraft defense, but ground artillery still could not use proximity fuses against enemy troops. Army artillery officers were furious. They knew the technology would be devastating. A shell detonating 70 feet above ground would kill anything in the open. But Pentagon officials held firm. The risk of capture was still too high. Then, at 0530, on December 16th, 1944, Germany launched Operation Watch on the Rhine. 3 German armies attacked through the Ardennes forest in Belgium and Luxembourg. The attack achieved complete surprise. German armor punched through American lines and began driving west toward the Meuse River. The Battle of the Bulge had begun. American forces were in serious trouble. Colonel Oscar Alfred Axelson commanded the 406th Field Artillery Group near Monschau, Germany. At 0530, on December the 16th, 1944, he received panicked radio calls from the 38th Cavalry Squadron. The lightly armed cavalry troopers were being overrun by German infantry. They needed artillery support immediately, or they would be annihilated. Axelson had exactly what they needed. Sitting in ammunition storage bunkers behind his position were crates of brand-new artillery shells marked with red bands and the code name POSIT. These were proximity fuse shells. Axelson knew they were classified at the same level as the atomic bomb. He knew Supreme Commander Dwight Eisenhower had not authorized their use over land against ground targets. He knew that using them without authorization could result in a court-martial. The 38th Cavalry Squadron was dying. Regulations could wait. Axelson ordered his gun crews to load the proximity-fused shells and open fire. Minutes later, the first POSIT rounds screamed over German positions and detonated 70 feet above the ground. The German infantry, advancing on the cavalry squadron, suddenly found themselves engulfed in steel rain falling from above. Foxholes offered no protection. Log-reinforced bunkers were penetrated by fragments. Men who had felt safe in covered positions were cut down by explosions they could not see coming. The German attack stalled immediately. What Colonel Axelson did not know was that he had just fired the first land-based proximity-fused artillery shells in the European theater against ground forces. And what the Germans being killed by those shells did not know was that they were facing a weapon their best scientists had declared impossible to build. By December 19th, General Dwight Eisenhower formally requested authorization to use proximity-fused artillery shells across the entire European theater. The German offensive was the largest attack the United States Army had ever faced. Every advantage mattered. On December 21st, all restrictions were lifted. Proximity-fused artillery shells were released for general use. The timing was critical. German forces were attacking the town of Malmedy. American artillery battalions supporting Malmedy fired proximity fuses with devastating effect. German soldiers caught in the barrage found themselves in airbursts that detonated overhead with no warning. Some Germans charged directly into the artillery fire with their hands raised, screaming, "Kamerad," the German word for comrade, trying to surrender to explosions they could not escape. By December 23rd, estimates suggested as many as 2,000 German soldiers had been killed by proximity-fused artillery shells in just the first few days of their use. The Germans quickly realized they were facing a new type of weapon. Prisoners of war repeatedly described the demoralizing effect of artillery shells that exploded in the air above them with perfect timing. Traditional artillery gave soldiers a brief moment of hope. They would hear the whistle of incoming shells and dive for cover. If they were in a trench or foxhole, they might survive even a direct hit nearby because the explosion occurred on the surface. But proximity-fused shells detonated 30 to 50 feet in the air directly above defensive positions. There was no cover. There was no warning. The shells arrived silently at high velocity and detonated overhead, raining shrapnel straight down. Soldiers who had felt safe in prepared defensive positions were being killed without ever understanding the threat. The psychological impact was severe. German commanders offered rewards for any soldier who could recover an intact proximity fuse. They needed to understand how the weapon worked so they could develop countermeasures or copy the technology. In late December 1944, German forces captured an American ammunition dump containing 20,000 proximity-fused artillery shells. German engineers examined the fuses carefully. They recognized that sophisticated electronics were involved. They could see miniature vacuum tubes, battery components, complex circuitry, but they could not understand how the technology worked. Most critically, German engineers could not believe that miniature vacuum tubes could survive the acceleration forces of artillery gunfiring. Their own research had convinced them that such tubes were impossible to manufacture. The acceleration forces would destroy them instantly. When German scientists examined the captured American fuses, they assumed the fuses were defective or designed for a different application. They never realized what they were looking at. By the time German engineers understood the significance of proximity fuses, the war was nearly over, and Germany had no industrial capacity left to develop countermeasures. The German scientific establishment had been correct about the technical challenges. Building vacuum tubes that could survive 20,000 GMO forces was extraordinarily difficult. What they had failed to understand was that difficult did not mean impossible. American engineers had solved the problem through systematic iteration. Test thousands of tube designs, identify failure modes, redesign, test again, fail again, redesign again, repeat until success. This approach required manufacturing capability that Germany lacked. By 1944, American industry was producing proximity fuses at scales Germany could not match. On the night of December the 25th and 26th, 1944, General George Patton's Third Army caught a German battalion attempting to cross the Sauer River near Echternach, Luxembourg. American artillery units fired a concentrated barrage using proximity-fused shells. The shells detonated above the river, and the German troops massed on the banks. There was no cover on the riverbank, no place to hide. The German soldiers were completely exposed. Patton wrote a letter to the War Department describing the result. The new shell with the funny fuse is devastating. We caught a German battalion which was trying to get across the Sauer River with a battalion concentration and killed by actual count 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I'm glad that you all thought of it first. 702 confirmed German dead in a single artillery barrage. That was unprecedented lethality. Conventional artillery shells might have killed 50 or 60 soldiers under similar circumstances. The proximity fuse had multiplied the effectiveness of American artillery more than 10 times. And this was not an isolated incident. Throughout the Battle of the Bulge, proximity-fused artillery devastated German formations caught in the open. In the Hürtgen forest, an American ordnance officer reported finding 96 bodies from a German patrol hit by a massed proximity-fused artillery barrage. The bodies, he wrote in his report, looked as if they had gone through a meat grinder. The high-velocity artillery shells arrived too quickly for German soldiers to hear them coming. The air bursts detonated with no warning. Foxholes provided no protection. The shrapnel even penetrated log-reinforced bunkers that would have stopped conventional artillery. German units that tried to advance through artillery fire were annihilated. German commanders reported that their soldiers were refusing orders to move forward because they knew proximity-fused artillery could kill them even in covered positions. Prisoners of war interviewed after capture described being in a dazed state after surviving proximity-fused barrages. They realized they were facing a new kind of artillery, but could not understand how it worked or how to evade it. Minor mutinies broke out among German units that were ordered into areas known to be covered by American artillery. Some German soldiers simply refused to leave their bunkers when proximity-fused artillery was falling. The Germans had felt safe from traditional timed artillery because heavy overcast weather prevented accurate aerial observation. American forward observers could not see German positions clearly, which meant timed artillery shells would be set based on estimates that were often inaccurate. German troops had learned to take cover whenever they heard artillery fire and wait for the barrage to end, but proximity-fused shells did not require accurate observation. The fuses automatically detonated at the optimal height above ground, regardless of weather conditions or visibility. American gunners just needed to know the approximate location of German forces and fire. The proximity fuses handled the rest. The bad weather that had protected German forces now meant nothing. By late January 1945, German resistance in the Ardennes had collapsed. The Battle of the Bulge was over. American forces had stopped the largest German offensive of the war and were preparing to cross the Rhine River into Germany. Proximity-fused artillery had played a critical role in that victory. Patton later stated that the funny fuse won the Battle of the Bulge for us. While that was an overstatement, the proximity fuse had undeniably changed the tactical situation. German forces that would have been able to defend prepared positions effectively against conventional artillery were wiped out by airbursts they could not avoid. In the Pacific theater, the proximity fuse had an even more dramatic impact. By 1945, Japanese forces had adopted kamikaze tactics, using suicide aircraft loaded with explosives to attack American ships. These attacks were extremely difficult to defend against because conventional anti-aircraft fire required direct hits on aircraft that were deliberately trying to crash into ships at close range. Kamikaze pilots often approached at wave-top altitude, making visual detection difficult. They would then pull up sharply for their final dive, giving gunners only seconds to engage. But proximity-fused shells created a defensive barrier around ships that was almost impossible for kamikaze aircraft to penetrate. The shells did not require direct hits. A near miss was as lethal as a direct hit. Navy studies showed that ships using proximity-fused ammunition were 5 to 10 times more effective at stopping kamikaze attacks than ships using conventional time-fused shells. Ships equipped with 5-inch 38 caliber guns firing proximity-fused ammunition could create a lethal zone extending thousands of yards from the ship. Any aircraft entering that zone faced a statistical probability of destruction that approached certainty. In the 7 months from January to July 1945, American ships expended nearly 2/3 of all proximity fuses used during the entire war. The proximity fuse allowed the Navy to maintain operations in waters where kamikaze attacks would otherwise have made naval operations suicidally dangerous. The effectiveness of proximity fuses went beyond simple statistics. The psychological impact on enemy forces was significant. Japanese pilots knew that approaching American ships equipped with proximity-fused anti-aircraft guns meant flying into an invisible sphere of death. The shells did not need to hit them directly. They just needed to pass nearby and detonate. There was no way to evade this defense. Japanese pilots reported feeling helpless against weapons that seemed to anticipate their maneuvers. The proximity fuse demonstrated a pattern that repeated throughout World War II and beyond. Technological advantage in warfare does not come primarily from theoretical breakthroughs. It comes from engineering execution and manufacturing scale. The concept of a proximity fuse was well understood by multiple nations before the war began. Germany, Britain, Japan, and the United States all explored proximity fuse designs during the 1930s. What separated success from failure was the ability to solve thousands of small engineering problems, manufacture components to precise tolerances, and produce complex electronic devices in quantities of millions while maintaining quality control. The United States had the industrial base, the skilled workforce, and the organizational structure that could coordinate work across dozens of contractors. Germany and Japan did not. By 1944, American industry was producing more proximity fuses every month than Germany and Japan had produced artillery shells of all types combined. General George Patton had been correct when he wrote that armies would need to devise new methods of warfare once proximity-fused artillery became widespread. The assumption that soldiers in trenches or foxholes were safe from artillery fire had been fundamental to military tactics since World War I. The proximity fuse shattered that assumption. Defensive positions that had been considered adequate protection against artillery were now death traps. Armies would need to disperse more widely, dig deeper fortifications, and move faster to avoid artillery barrages. The tactical changes forced by proximity-fused artillery rippled through military doctrine for decades. Section T, the organization that developed the proximity fuse, operated on an accelerated timeline that would have seemed impossible in peacetime. From the initial assignment in August 1940 to the first combat use in January 1943 was less than 2.5 years. During that time, Tuve's team had solved problems that had stumped scientists in multiple countries for more than a decade. They had developed miniature, ruggedized vacuum tubes that could survive forces no civilian electronics had ever faced. They had designed circuits that operated reliably under conditions of extreme vibration, temperature variation, and electromagnetic interference. They had created manufacturing processes that could produce complex electronic devices at scales previously thought impossible. And they had done all of this while maintaining absolute secrecy that prevented enemy intelligence from learning what they were building. Dr. Merle Tuve never received public recognition for leading the development of the proximity fuse during the war. The project remained classified until after Japan surrendered. Even after the war ended, Tuve was reluctant to discuss his role. He understood that Section T had solved an engineering problem that saved thousands of Allied lives. But he also knew that many people at many organizations had contributed to that success. The proximity fuse was not the work of a single genius. It was the product of systematic collaboration between physicists, engineers, manufacturers, and military personnel across dozens of organizations. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Over 22 million proximity fuses were produced during World War II by more than 100 manufacturers. That scale of production required contributions from thousands of people, most of whom never knew what they were building. After the war, Tuve returned to the Department of Terrestrial Magnetism at the Carnegie Institution and served as its director from 1946 to 1966. He continued research in geophysics and radio astronomy. In 1948, he was named an honorary commander of the Order of the British Empire for his service to the Allied cause during the war. President Harry Truman awarded him the Presidential Medal for Merit. But Tuve rarely spoke about the proximity fuse. When asked about his wartime work, he emphasized the collaborative nature of the project and the contributions of engineers and technicians who had solved countless technical problems that made mass production possible. Dr. Merle Tuve died on May 20th, 1982 at the age of 80. His obituaries mentioned his contributions to geophysics and his leadership of the Applied Physics Laboratory during World War II, but most did not detail the specific work he had done on proximity fuses. The technology had been declassified for decades, but it remained obscure outside military and technical circles. Tuve himself had never sought publicity for his wartime work. He believed that scientific achievement should be measured by results, not recognition. The proximity fuse had saved lives and helped win the war. That was what mattered. The Applied Physics Laboratory that Tuve founded continues to operate today as a research facility of Johns Hopkins University. It conducts work in national security, space exploration, and advanced technology development. The building in Silver Spring, Maryland, where Section T first assembled proximity fuses in 1942, no longer stands. It was demolished decades ago and replaced by commercial development. There is no memorial marker at the site. Nothing identifies it as the place where one of the war's most important technologies was born. The workers who assembled proximity fuses in factories across America went back to their peacetime jobs when the war ended. Most never learned exactly what they had been building. The soldiers and sailors who benefited from proximity-fused ammunition rarely knew the technical details of how the fuses worked. They just knew that anti-aircraft guns were suddenly much more effective and artillery barrages were far more lethal. The technology remained mysterious, even to the people whose lives it saved. The 702 German soldiers killed by proximity-fused artillery on the banks of the Sauer River in December 1944 were buried in military cemeteries in Luxembourg and Germany. Their graves do not mention how they died. The military records list them as killed in action by artillery fire, which was true but incomplete. They were among the first ground troops anywhere to be killed by a technology that their own scientists had declared impossible. They died, not knowing that the shells exploding above them contained miniature radar sets more sophisticated than anything Germany had been able to build. They died not knowing that American factories were producing these shells by the hundreds of thousands, while German industry struggled to manufacture basic artillery ammunition. The German engineers who had declared proximity fuses impossible never understood what they had missed. After the war, American technical intelligence teams interrogated German scientists and showed them captured German documents detailing their proximity fuse research. The Germans had explored most of the same technical approaches that Section T had used. They had considered radio frequency fuses, vacuum tube designs, and miniaturization techniques, but they had concluded that the engineering challenges could not be overcome with existing technology. What separated the American project from the German project was not a difference in scientific knowledge, but a difference in engineering persistence and manufacturing capability. American industry could produce miniature ruggedized vacuum tubes in quantities of millions. American engineers could iterate through dozens of design failures until they found solutions that worked. Germany lacked the industrial base and the time to compete on those terms. British scientists who had contributed the initial circuit designs to Section T watched the American success with mixed feelings. They had solved many of the conceptual problems, but had been unable to scale up to mass production. The British proximity fuse program produced working prototypes, but never achieved the reliability and cost-effectiveness needed for large-scale military deployment. When the Teesside mission delivered British proximity fuse designs to Section T in August 1940, they gave the Americans a starting point. But, as Tuve later noted, the circuit design that Section T made work was substantially different from the British design. American engineers had redesigned nearly every aspect of the fuse to meet Navy specifications and survive the brutal forces of artillery gunfiring. This is how wars are actually won, not through dramatic breakthroughs or genius inventors working in isolation, but through systematic collaboration between scientists, engineers, manufacturers, and military personnel. The proximity fuse succeeded because a Section T could draw on the resources of American industry, the technical expertise of academic researchers, and the practical knowledge of Navy ordnance officers who understood what combat conditions would demand. It succeeded because Western Electric and Raytheon could manufacture ruggedized vacuum tubes that no one had built before. It succeeded because factory workers across America could assemble complex electronics at scales that would have been impossible for any other nation. And it succeeded because Colonel Oscar Alfred Axelson made the decision to use the technology when it mattered most, even though he was violating direct orders by doing so. The story of the proximity fuse is the story of American industrial and scientific power at its peak. It is the story of what becomes possible when capable people are given clear objectives, adequate resources, and freedom from bureaucratic constraints. It is the story of innovation that happens not through individual genius, but through systematic problem-solving at scale. And it is the story of a technology that saved thousands of Allied lives and changed warfare forever, developed by people whose names are mostly forgotten today. German soldiers, throughout the Battle of the Bulge, reported the same experience. Artillery shells that arrived without warning and detonated overhead with perfect precision. No time to take cover, no protection from foxholes or trenches, shrapnel falling straight down from explosions they could not see. Many German prisoners described feeling helpless, facing artillery that seemed to know exactly where they were and exactly when to explode. Some German units refused orders to advance into areas known to be covered by American artillery. The effectiveness of proximity-fused shells exploding in mid-air on exposed personnel caused what intelligence reports described as minor mutinies when German soldiers started refusing orders to move out of their bunkers during an artillery attack. The demoralizing effect cannot be overstated. German infantry, who had survived years of combat on the Eastern Front, who had endured Russian artillery barrages involving thousands of guns firing simultaneously, reported that American proximity-fused artillery was more terrifying than anything they had experienced. Russian artillery was heavier in total volume. Mass batteries firing hundreds of guns could devastate entire sectors. But Russian artillery lacked flexibility and rapid response capability. Once a barrage plan was set, it could not be adjusted quickly. American artillery at the Battle of the Bulge was different. It combined mass with responsiveness. Individual American batteries were no more powerful than German or Russian equivalents. The 105mm howitzer, the standard American divisional artillery piece, had similar range and shell weight to German equivalents. But American batteries could respond to calls for fire within minutes. They could shift targets rapidly, and they could deliver proximity-fused strikes that arrived without warning. German after-action reports from units that fought in the Battle of the Bulge repeatedly emphasized the speed and accuracy of American artillery. Commanders noted that American forward observers seemed to be everywhere, calling fire on any German movement. Assembly areas that should have been safe from observation drew accurate fire within minutes of troops gathering. Approach routes that German planners had identified as concealed from direct observation were still targeted precisely. Part of this was superior American observation capabilities. American forward observers were well-trained, well-equipped with radios, and integrated directly into infantry units at company and battalion level. They could call for fire from any battery in range, not just batteries organic to their division. This meant a forward observer from one division could request support from another division's artillery or corps-level guns. The system treated all artillery as general support rather than being rigidly allocated to specific units. But observation alone did not explain the coordination speed or the devastating effect of the artillery that arrived. What German intelligence never discovered was that the shells themselves were doing the work of detecting targets and choosing the optimal moment to detonate. The proximity fuse was hidden in plain sight. It was a small electronic device in the nose of a shell. Even if captured intact, it might not be recognized as significant. It looked like mechanical components and electronics. Only someone who understood American artillery doctrine and the specific technical challenges of proximity fuse development would realize it was the key to American artillery's superiority. German artillery doctrine still relied on pre-plotted concentrations. Before an offensive, German artillery officers would survey positions, calculate firing data for planned target areas, and prepare detailed fire plans. During the actual battle, batteries would execute these pre-prepared plans. This worked well for set-piece attacks where the sequence of targets was predictable, but it was inflexible. If the tactical situation changed, if targets moved, if unexpected targets appeared, German artillery could not respond quickly. Fire direction centers had to recalculate using tabular methods, which took minutes. By the time fire arrived, the target had often changed. American artillery operated completely differently. Forward observers identified targets in real time. Fire direction centers calculated new data for each mission. Batteries could shift from one target to another in under 2 minutes. The entire system emphasized flexibility and speed over detailed pre-planning. The psychological impact on German soldiers was severe. Traditional German infantry doctrine assumed that artillery preparation would precede attacks, and that defending artillery would respond gradually, allowing attackers time to close with defenders under covering fire from their own artillery. At the Battle of the Bulge, those assumptions failed. American artillery did not wait. American guns fired first, accurately and devastatingly. German infantry advancing toward American positions were hit by concentrated fire before they could deploy effectively. The 12th SS Panzer Division, Hitler Jugend, had been formed in 1943 from Hitler Youth members. Fanatically motivated and exceptionally well-trained, they considered themselves elite troops. At Elsenborn Ridge in Belgium, during the Battle of the Bulge, they broke against American defenses and suffered such heavy casualties that the division was combat ineffective. By December 23rd, German commanders had to pull them out of the line. An elite SS Panzer Division stopped cold by American artillery and infantry fighting from defensive positions. The failure at Elsenborn Ridge forced fundamental changes to the German offensive plan. The original concept required the 6th SS Panzer Army to make the main penetration in the north, seize the Meuse River crossings, and drive on Antwerp. When the 6th SS Panzer Army stalled at Elsenborn Ridge, unable to secure the road network it needed, Hitler redirected effort to other sectors. This meant attacking through more difficult terrain with fewer roads. The offensive lost cohesion. Instead of a concentrated thrust with clear objectives, German forces were spread across multiple axes without sufficient strength for decisive breakthrough anywhere. By early January 1945, the Bulge was being compressed from both sides. By the end of January, the Germans had been pushed back to their start lines, having achieved nothing except enormous casualties they could not afford. The Battle of the Bulge was the largest battle ever fought by the United States Army. Over 600,000 American troops participated. American casualties exceeded 83,000, including 19,000 killed. But the Germans lost 100,000 casualties, 600 tanks, and hundreds of aircraft. More importantly, they lost their last mobile reserves and their last chance to avoid total defeat. After the Bulge, Germany's defeat was inevitable. The proximity fuse had not won the battle alone. But it had multiplied the effectiveness of American artillery to the point where German forces could not mass for offensive operations without being devastated by airbursts they could not avoid. Trenches became death traps. Assembly areas became killing zones. The initiative shifted completely to the Americans. One infantry company commander in the 2nd Infantry Division said he felt like he had the entire United States Army's firepower available whenever he needed it. That was not an exaggeration. The artillery coordination system meant that any forward observer could call for fire and receive support from any battery in range. It did not matter which division the battery belonged to, and all artillery was coordinated through centralized fire direction centers. All batteries could calculate firing data rapidly. All proximity-fused shells would detonate at the optimal height automatically. This level of coordination was unprecedented. British artillery used similar techniques, but could not match American speed and flexibility. German artillery was still largely horse-drawn, could not keep up with mobile operations, and lacked the communication networks for rapid coordination. Russian artillery had massive firepower, but relied on pre-planned barrages, not responsive fire support. American artillery at the Battle of the Bulge set a new standard for what concentrated firepower could achieve. The irony was that the technology enabling this revolution was so simple. Miniature vacuum tubes, a basic radio transmitter and receiver, a battery activated by firing shock, safety mechanisms using mercury switches and timers. These components, properly engineered and manufactured at scale, gave American artillery overwhelming superiority. German forces could not counter it because they could not see it. The proximity fuse was hidden inside artillery shells. Nothing visible on the battlefield revealed why American artillery was suddenly so much more effective. German intelligence tried to determine what had changed. They examined captured American positions. They interrogated prisoners. They analyzed tactics. But they found nothing obvious. American guns were the same models they had faced for months. American ammunition looked the same. Radio equipment was standard. The Germans never discovered that the change was a fist-sized electronic device in the nose of each shell that made the shell itself intelligent enough to detonate at the optimal moment. The workers who built proximity fuses never knew how many lives they saved. The soldiers whose lives were saved never knew the names of the physicists and engineers who made it possible. Dr. Merle Tuve, who led Section T and solved the fundamental engineering challenges, received official recognition but little public fame. The proximity fuse was one of the three most important technological developments of World War II, alongside radar and the atomic bomb. But while radar and the atomic bomb captured public imagination, the proximity fuse remained obscure, perhaps because it was too technical to dramatize easily, perhaps because its contribution was multiplicative rather than singular. The proximity fuse did not win battles by itself. It made every artillery barrage more effective. It made every anti-aircraft gun more lethal. It saved lives gradually, engagement by engagement, throughout 2 years of combat in multiple theaters. Secretary of the Navy James Forrestal said the proximity fuse helped blaze the trail to Japan. Without the protection this ingenious device gave the surface ships of the fleet, our westward push could not have been so swift, and the cost in men and ships would have been immeasurably greater. Winston Churchill said the proximity fuses, made in the United States, proved potent against the small unmanned aircraft with which Britain was assailed. In 1944, General George Patton said the funny fuse won the Battle of the Bulge for us. All of these assessments were correct within their scope. The proximity fuse had been critical in all these contexts, but the full story was more complex. The proximity fuse succeeded because American industry could manufacture millions of complex electronic devices while maintaining quality. It succeeded because American engineers solved thousands of small technical problems through systematic iteration. It succeeded because American military doctrine emphasized flexible, responsive fire support rather than rigid pre-planning. And it succeeded because when German scientists declared proximity fuses impossible, American scientists did not accept that conclusion. They tested, they failed, they redesigned, they tested again. They kept working until they succeeded. That persistence, backed by industrial capacity and organizational capability, made the difference. The Germans felt safe from timed artillery fire because bad weather prevented accurate observation. They were wrong. The Americans did not need observation. The shells observed themselves. The Germans felt safe in foxholes and trenches because artillery shells detonated on the ground. They were wrong. The shells detonated 70 feet overhead. The Germans thought miniature vacuum tubes could not survive artillery gun firing forces. They were wrong. American engineers had made it work. These errors cost Germany tens of thousands of casualties and contributed to the failure of their last major offensive. The soldiers who died never knew what killed them. They heard no warning. They saw no incoming fire. They simply found themselves engulfed in explosions from above with no time to react and no way to survive. That is what technological superiority looks like in warfare. Not dramatic wonder weapons or science fiction concepts, but engineering excellence applied systematically at scale. The proximity fuse was a miniature radio in a shell. That simple description understates the engineering required to make it work. But it captures the essential truth. American physicists, engineers, and factory workers turned a simple concept into a weapon that changed warfare. They did it in less than 3 years. They produced 22 million units. And they kept it secret until the war was won. German gunners were terrified when American proximity fuses exploded shells 70 feet above their heads because they had no defense against this weapon. There was no tactical response, no countermeasure, no way to adapt. They could only hope that American artillery would not target their position, and when it did, they could only die. That psychological impact, the knowledge that any open area could become a killing zone, instantly with no warning, broke the will of units that had previously been considered elite. The SS soldiers who refused to leave their bunkers during proximity-fused artillery barrages were not cowards. They were experienced combat veterans who understood they were facing something for which their training had not prepared them, something their commanders could not counter, something that made all their defensive tactics obsolete. The proximity fuse did not make artillery more destructive in absolute terms. It made artillery more efficient. Every shell that would have been a near miss became a kill. Every barrage that would have scattered became concentrated. The overall effect multiplied American artillery effectiveness by a factor of 3 to 10, depending on the target type and circumstances. That multiplication was decisive. Germany could not afford the casualties. By late December 1944, German forces were already weakened by years of combat on multiple fronts. Every soldier killed by proximity-fused artillery was a soldier who could not be replaced. Every unit shattered by airbursts was a unit that could not continue offensive operations. The cumulative effect helped turn the Battle of the Bulge from a German opportunity into a German disaster. This is how technological advantages compound in warfare. One innovation enables better tactics. Better tactics force the enemy to adapt. The enemy cannot adapt quickly enough. Casualties mount. Morale declines. Offensive capability degrades. The side with the technological advantage gains initiative. The side without it loses options. The gap widens until one side can no longer compete effectively. The proximity fuse was not the only American technological advantage in World War II, but it was one of the most significant because it affected every artillery engagement and every anti-aircraft battle from January 1943 until the end of the war. Millions of proximity fuses were fired, hundreds of thousands of enemy soldiers and aircraft were killed or damaged by them. The cumulative effect was enormous. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.